Susan and Annika, Luis, and Simon for organizing this nice workshop seminars. Okay, so today I have the pleasure to start this workshop, and I'll do so with I think relatively light talk. I don't have too much material, and it's mostly based after a small review on some old work here that I did with my former EPFL collaborators, Anton de la Fuente, Sasha Monin, David Pirtskhalava, and Riccardo Rattazzi, and on some new results which are unpublished that are still in progress with, based on discussion with Zohar. Okay, so let me get started. So the overview of my talk is the following. I'll start with some basic introduction, some review of which I think is well suited for the first talk of the workshop, of the construction of San Domenico, Edelman, and Watanabe for large charge operators. And then the main body of the talk will be about extending the results of the large charge expansion to operators which are spinning, so they have some spin, in focusing essentially on three-dimensional conformal field theories. And I'll finally summarize a bit the results, open and have some time for questions. As I said, please feel free to interrupt me at any moment. Okay, so the reason why we are here is that we're interested in studying general properties of quantum field theories, and this often means properties of conformal field theories. This because are somewhat more controlled examples, and scale invariance is always very useful tool. And here starts an issue that most theories are kind of strongly coupled, and we don't know how to analyze them systematically in the absence at least of some more powerful properties, such as extended supersymmetry, for instance. Nonetheless, there are some situations, some observables for which a natural perturbative expansion emerges. And this is generically the case whenever you consider states with large quantum numbers. So the most notable examples is the large spin expansion in CFTs. I think originally proposed, at least somewhat systematically, in a picture by Alda and Maldacena, but then remarkably analyzed within the last 10 years by the conformal bootstrap. The case that I think is most relevant for this workshop is the one of large internal charges under some internal symmetry of the theory. And this has been first analyzed by Hellerman, Orlando, Reffert, Watanabe in 2015. And also the regime of large scaling dimension is somewhat admits some universal properties, normally in the form of heavy, light, heavy 3-point functions, which are related to some thermodynamic behavior of the theory and sometimes hydrodynamic behavior. So the key observation which underlies all of these regimes is that operators with large quantum numbers in CFTs by the state operator map can be precisely associated with states for the theory quantized on the cylinder. And then we can try to guess what is the form of this state and whether it admits some universal features. In the case of large spin, this was done by Alda and Maldacena. And the idea is that there are some class of operators that resembles pretty much free moving particles which are fastly spinning on the cylinder. And so the picture is not very well done. They should be at antipodal points. To leading order, the energy of such state will be just given by the free energy of the particles. And this just gives you the J plus twice the mass of the particles. But there are corrections to these pictures. And the key insight of Alda and Maldacena was to show that these corrections are actually suppressed in the large spin regime. This is because you can think of these operators as in a gap theory where the gap is given by the twist of the operators exchanged of the operators that these two states can exchange. And they managed to show via some conformal mapping that the separation which is relevant in this gap theory is related to the logarithm of the spin. And therefore they obtained that corrections to the free picture for the states scale like 1/j times the minimal twist gap of the theory. So in theories with a twist gap, large spin operators are approximately free. And this is always the case in CFT in d bigger than 2. The picture which underlies the large charge expansion is similar, but the setup, of course, is slightly different. In this, to consider now again as d-dimensional CFT, but with an internal symmetry group G, and calling Qi the global Cartan charges of G, possibly plus spin. The idea is to consider operators which are charged under these Cartan charges, and in particular, calling the lowest dimensional operator as some fixed values of the Cartans, or Q. We can compute semi-classically correlation function of this form. So you have an insertion of OQ, an insertion of its conjugate. So this is kind of a state and its conjugate states if you map to the cylinder. And then you can additionally consider some light operators insertions in between. And this correlation function will admit some universal form. Okay, so let me review how this comes about. So as I said, the basic point is to consider a state. So we should ask what are the properties of this state. So as usual, I'll focus for simplicity on theories with U1 symmetries, but I should say here there are many words for non-abelian theories. So this is not an enormous restriction. And ask what are the properties of the ground state at fixed value of the charge. So one thing for sure is this state will have some charge density, and the charge density for the theory quantized on the cylinder naturally sets a scale mu, where R here is the radius of the sphere, which I keep for dimensional analysis. In the limit of large charge, the charge density sets a mass scale which is much larger than the geometric scale of the theory, therefore suggesting that some stuff can become gapped, and perhaps you may have a simplified description in terms of some degrees of freedom. In particular, this state with finite charge density, as well known in condensed matter physics, must realize non-linearly all these space-time symmetries. This means that just by the presence of the charge, some symmetries will be broken, and therefore there will be some Goldstone bosons. And we know very well how to write effective field theory for Goldstone bosons. And in the condensed matter language, these are just the low energy hydrodynamic modes. I refer you to this nice paper 2015 for a detailed account of this correspondence. So, well, now, how is the space-time symmetry group and internal symmetry group realized by this large charge state? Well, we don't have that many options. Let me start making the assumption that this state is homogeneous, so that the charge density is spread homogeneous. This corresponds to the physical intuition that in many models, the lowest dimensional operator of fixed charge will be a scalar. For instance, we believe this is the case in the O2 model in 3D. Then, I mean, the full space-time symmetry group will be broken purely to the rotation group and perhaps time translation. So rotations group are like translation on the sphere, of course, and time translations is just the dilation on the sphere. So the question which remains is whether the U1 symmetry is broken or unbroken. So one of the main insights of the paper of Hellerman, Orlando, Leffer, and Watanabe is that generically, this U1 symmetry will be broken. And will be broken in such a way to leave a stationary trajectory, meaning that the U1 will be broken, so Q will be broken, the time translation generator will be broken, but the linear combination d bar equal d plus mu q will be preserved. This is just what defines the superfluid. And the low end and a conformal superfluid may well be described in terms of a single U1 Goldstone boson at low energy, which is expanded around a configuration which is linear in time, and pi of x is just the hydrodynamic mode. All the other modes in the simplest option will be gapped at the largest scale in the game, which is just set parametrically by the density, and it's just Q1 over D minus 1 divided by R. Of course, there are exceptions to this rule, and they can be arise either because of some fine tuning or more interestingly, because of additional symmetries as it happens in superconformal field theories, which have been analyzed in a series of papers by Hellman, Med, Orlando, Leffer, Watanabe. But okay, I won't talk about superconformal field theories, but anyhow, the point is that now we can write systematically the Lagrangian describing our stated excitations in a derivative expansion, pretty much as we do with the pion Lagrangian QCD. Okay, so let me start with something now slightly more concrete, and this is the Lagrangian. So this Lagrangian is derived just by imposing chi is the Goldstone I showed before, so it's a shift symmetric scalar. And the higher derivative terms here are just obtained by imposing Weyl invariance and by imposing Weyl invariance and diffeomorphism invariance. And okay, so actually here there is a typo. There should be some completion to this term, but it's not important. So you notice right away that on the background is chi equal mu t. The first term scale like mu to the d, which if you translate in powers of q, scales like qd over d minus 1. The second and third term, they scale like mu to the d minus 2. And again, in powers of q, it just corresponds to qd minus 2 times d minus 1. So you see they are suppressed. And so forth, so on for the other operators you can write in this effective theory. Therefore, you see that as long as q is sufficiently large, you have a well-defined perturbative derivative expansion. Now you can use this action to make some predictions for the theory. And the simplest thing you can compute is the energy of the ground state, which corresponds to the scaling dimension of the lowest dimensional operator of fixed charge. So you see it's given in an expansion in powers of q2 over d minus 1, with the leading term scaling like qd over d minus 1, as you could have guessed from the action. The coefficients alpha 1 and alpha 2 are related to the Wilson coefficients here. And of course, they are not fixed by symmetry, so ultimately depend on the microphysics, on the specific model. And additionally to this classical expansion, you can also compute quantum corrections. The loop counting parameter, of course, is given by the classical value of the action. So it's qd over d minus 1. Therefore, the one loop correction will scale like q to the 0. And two loops will be additionally suppressed. And now you notice something interesting, that this in odd dimension, in particular in d equal 3, the expansion runs in q to the 3 half times q to the 1 half times plus q to the minus 1 half and so forth, so on. So there is nothing which can renormalize the one loop correction. Correspondingly, once you compute it, you must find a finite result, which is universal. And that's what you find. You find a number. It's just a Casimir energy. And okay, this is the number. You have to compute it numerically. And it's very interesting because this one loop correction is a universal prediction independent of the theory. And this was noted in the original works. For even space-time dimension, instead, the expansion run difference, you do have a term scale like q to the 0 in the classical expansion. So for instance, in even space-time dimension, you have q to the 4/3, q to the 2/3, q to the 0, and so forth, so on. Therefore, it might seem that the one loop correction is actually not calculable, but of course, as usual in these cases, whenever you have a whenever you can renormalize an observable, this means that you have a predicted powers on the log rate of the cutoff, which arises in the one loop calculation. And that's what happens also here. You have a log q term. Remember, the cutoff is set parametrically by mu, which is set parametrically q1 over d minus 1 by r. So up to some powers of d and a number that you have to compute. You can guess that in d equal 4, you must have a log q quantum correction, which is independent of the Wilson coefficients. That's what you find, and that's the number. Now it's also very easy to do something beyond the ground state energy. And to do so, you just expand your action. And of course, so conformal invariance fixes the sound speed of the hydrodynamic mode. since of course relativity is spontaneously broken by the density, you don't expect anymore to stop traveling at the speed of light. In fact, you don't find so. You find a sound speed which is 1 over d minus 1. And correspondingly, the excitations above the ground state have energy given by this formula here, where j plus d minus 2 is just the eigenvalue of the Laplacian on the sphere. And this tells you some non-trivial, this 0.1 QFT exercise tells you something non-trivial about the CFT spectrum. So that is now organized as a Fock space above the large charge ground state. In particular, the j equal 1 states just correspond to the creation of descendants, and you see this because they have energy equal 1. So they are what you expect from acting with a derivative on an operator. And you can check that by computing the nether charges in the theory. And the states with j bigger than 1 instead are new primaries for which you have non-trivial predictions. Okay, questions so far? Okay, so this is probably well known to everyone here. So, okay. So as I said, the goal of my talk today is try to tell you a story of how you can go beyond this simple picture to include operators with also large spin in the story. So the first thing, okay, let us now ask a question. So what is the ground state at large charge as we increase the spin? So what is the scaling dimension, for instance, of the lowest dimension operator with fixed charge and spin when both of them are large in some regime? And for the sake of concreteness, we can think about the three-dimensional two model to have a ground. So the first thing, of course, is to start from the superfluid and add phonons. And you have two ways to build a spin j state. You can add a phonon with spin j, or n phonons with spin j over n, well, or anything in between, but of course, these are the two natural options. It is easy to check that the state with a single phonon is more favorable with respect to the state with n phonons. However, this state is within EFT only as long as the derivative expansion is well posed. This means as long as j is much smaller than square root of q in the equal free. Things look slightly better for states with n phonons because you can sprinkle the spin over all of them. You can sprinkle them on the sphere. So as long as their number is much smaller than the charge and their individual spin is much smaller than the cutoff, you are within the derivative expansion. This means j much smaller than q to the 3 half if you do the calculation carefully. And then you might expect this behavior to extend, therefore, up to j or the q to the 3 half. And you might guess then, therefore, the energy of a state with large charge and large spin will be like alpha q to the 3 half plus something scale going linear in j. And then keeping only leading order both in q and j. But that doesn't sound right, at least not until j order q to the 3 half. And one way to see that is just to look at experiments. So we are talking about superfluids, even though in conformal field theories. And it's a very well-known fact that superfluids, once you make them spin, they do not, at some point, there is a critical value for which they start developing vortices. So you have your homogeneous superfluid, you make it spin, at some point you create a hole around which the superfluid spins. Then you create more holes, and so forth, and so forth, and so forth, so on. This is for Bose-Einstein condensing and magnetic trap in particular. Therefore, the natural thing to expect is that something like this should happen also for our large charge ground state in the O2 model. So the question is, how does this come about? So to see whether this is reasonable and to make predictions, we need to extend effective field theory, so to include vortices. And that's what I'm going to want to tell you now. So to start, it is convenient to dualize the theory from a purely scalar theory to a dual theory in terms of a gauge field. This is just the baby version of particle vortex duality. And okay, the coefficients C and kappa here are clearly related. And the explicit relation between the scalar and the gauge field is just obtained by matching the U1 current. So the U1 current on the left-hand side is just the current that you compute from another theorem. And on the right-hand side is instead the topological current for the gauge field. And therefore, the charge density maps to a monopole magnetic field background on the right-hand side. So this is what this formula here is telling you. Therefore, for physical intuition, while the cutoff now is set by the value of the monopole field. So particularly, this is precisely, if you think of your theorem, the sphere, this field here is precisely the one you obtain by placing a monopole at the center of the sphere. That's why it's called monopole field. So we now need to introduce the vortices. So what are vortices? Vortices are locations around which the superfluid spins and the effective field theory breaks down. So of course, at the vortex course, we cannot expect to have the same effective field theory description, just because there the superfluid density drops. So the natural thing to do is to introduce them as defects moving in the effective field theory. So in particular, or as well known, vortices can be thought as charged particles in the dual language. So to write the effective field theory for vortices is extremely easy. You just write the theory of a charged particle. So you have the gauge coupling to the gauge field, and then you have the standard word line action. So the gauge coupling you can show is nothing but the vorticity. So the QP here is quantized and provides exactly the vorticity of the particle. So the number of windings that the scalar does if you move around the vortex. The word line action has a mass, which is naturally set by value invariance, and it coincides essentially with the square root of the magnetic field, as you could have guessed by dimensional analysis. So it's written here. So now, what is the theory? So what happens to charged particles in a magnetic field? Well, as well known, they organize in Landau levels. And Landau levels are separated by the well-known cyclotron frequency formula B over M. But B over M is just square root of B, which is just cutoff. So this means that to have an effective field theory, we need to integrate out all the Landau levels, but the first. This is called the lowest Landau level sometimes. It doesn't matter. And so we have essentially our theory is a theory for particles in the lowest Landau levels in a magnetic field. If you're wondering what this means technically, well, this first term here, once you expand it, goes like a mu x dot mu d tau. So this goes like velocity for the vortices. This term here, up to a constant, goes like, okay, square root of b, 1 plus v square. So it goes like the velocity square of the particle if you expand a small velocity. So restricting to the lowest Landau levels means nothing but neglecting this v square p. So working at small velocity approximations for the particles. So essentially means neglecting the last piece I wrote down in this effective field theory for you. In fact, I could have started without ever writing this term, but I think pedagogical reasons would have not been very clear. Okay, and I should say, okay, the effective field theory for vortices was developed first in this modern language, at least actually in the 3+1 case by Horney, Collis, and Penko in 2015, even though, of course, many of these things were known since before. So, okay, what we did in this old work of 2017 was to analyze this setup and see what are the predictions for the CFT from the CFT. So to leading order, we just have a simple electrostatic problem. Now we have to decide how many vortices we place and how do they interact with the electrostatic field. So vortices, since I'm neglecting the piece which is velocity squared, they just move according to drift motion. This equation is just the typical Lorentz balance of the Lorentz force, E equal VB. Instead, at the same time, the charged particles, the vortices, will source an electrostatic field just according to Gauss law, where E squared just by the initial analysis turns out to be square root of Q parametrically. Therefore, if you combine these two equations, you see that you source an electric field which scales like square root of Q. And instead, vortices move very slowly, like 1 over square root of Q, at least when they are sufficiently far apart. So this justifies a posteriori the small velocity approximation I made before, or the lowest Landau level approximation I made before. And additionally, of course, Gauss law implies that on the sphere, you can only put an equal amount of vortices and anti-vortices. So the sum of the vorticity should be 0. It's just, if you solve this electrostatic problem on the sphere, now you can compute the energy and the angular momentum of the state for an arbitrary number of vortices. So you find that the leading order, of course, is the same one of the superfluid, which is unperturbed, alpha Q to the 3 alpha. But the leading correction will come from the electrostatic energy, and it goes like logarithm of the distance between the vortices. So Rp is the coordinate of the vortices in the R3 embedding of S2. So this is S2 embedded in R3. And so the reason why a log is because the Coulomb potential in 2 dimensions just scales logarithmically. It's just a solution of the plus equation in 2D. The log Q here comes because vortices have a self-energy. So a vortex interacts with itself. It has a self-energy diagram, which goes like E square logarithm of the cutoff, which is square root of Q log of Q parametrically. So if you combine this and use that the sum of the vorticities is 0, you can recast in this form the energy. So this sometimes goes to the fact that the fugacity of the vortex is classically normalized, sometimes people say. And instead, the angular momentum is just evaluated again. Classically, the angular momentum comes from the, I forgot the name, is the usual formula. J is the integral over space of E wedge B, at least in 3D, we would write something like this, divided by E square. So if you use this formula here and you use also Gauss law and that B is almost constant, you can show that the angular momentum is equal to Q alpha times the sum over the vortex locations. Equivalently, you can interpret this formula by saying that each vortex carries an angular momentum equal Q alpha times its vorticity. And this is a well-known fact that monopole harmonics on the sphere, they have an angular momentum equal half of the magnetic field, or the monopole magnetic field. So, but alternatively, classically, it just comes by evaluating this formula with B equal constant. Okay, so now you start a bit of these formulas and you try to figure out what is the ground state of the theory once you fix J and Q. And that's what we did. And at least in some cases, the answer is relatively easy. So the first setup you can work is J smaller than Q and much larger than the square root of Q. In this case, you have a vortex anti-vortex pair. The angular momentum is proportional to their distance on the sphere. And that's the picture. So due to the balance of the back magnetic and electric force, they move in circles on the sphere. And here there is also a stereographic projection. And they have minimal amount of vorticity. And okay, when J approaches square root of Q, their distance becomes very small and the effective field theory breaks down, simply because the closer the two vortices are, the faster they move and eventually become relativistic. So they exit the lowest Landau level description. But otherwise, they're within the FT, and then you can compute the energy, and you find this nice formula here. So this distance here really becomes, in the formula before, becomes J, and then you recast everything. And nicely, to leading order in Q and J, this formula depends on the unique parameter alpha. That's because the gauge interaction between the vortices and the electrostatic field doesn't depend on any new parameter in the FT. You can also go slightly beyond this classical description. I already said that every vortex carries an amount of angular momentum which is equal to Q half times the vorticity. And this makes it immediate to quantize the system, because you just take each vortex coordinate in their free embedding and you impose the SU2 algebra. Of course, you can derive this by properly quantizing the Lagrangian, but it's essentially obvious to guess this formula. This implies that at the quantum level, the vortex coordinates are non-commuting coordinates, and that's why sometimes this system is called fuzzy sphere. And you can immediately use this fact to find quantum corrections to the formula I showed before. And they just amounts to replacing the J square in this logarithm with JJ plus 1. So, okay, there is one among many subleading corrections, but you can show it's a functionally distinguished one. So it's observable in principle. Okay. So finally, you want to go J much larger than Q. And it turns out that it's more convenient, rather than increasing the vorticity, to have many vortices. That's because of the logarithmic fugacities of the vortices, so the square root of Q log Q term. So you just approximate the vortex distribution with some smooth function, and you minimize in terms of this smooth function the energy at fixed J. You find a vortex density going like J over Q. And so with and like cosine theta, so like you have positive vortices on the upper half of the sphere and negative vortices on the lower half. And you find this formula for the energy. Again, it depends on a unique parameter alpha, and it holds in this regime. So if you compute the angular velocity of the sphere, you find this, that it is moving the superfluid with constant angular velocity like a rigid body. This is very nice because it matches what happens in experiments. You know, once you put a superfluid in a trap and you make it spin, at some point it develops a vortex lattice, which moves precisely with the behavior of a rigid body. So that's something very similar happens here. And that's why also you might want to call this configuration a vortex lattice or solid. But okay. And the question we recently asked was, can one go beyond this regime? So a priori, you might guess this is not the case, because as J approaches Q to a 3/2, then you find that the angular momentum approaches the scaling dimensions. You might think you're already in the regime of the analytic bootstrap, that generically, at least for small q, applies when delta is of order J. But I think it's not clear how this transition should happen. It's not clear what would happen to the superfluid and the vortices in this setup. So I think it's more natural to think that there should be a new state in between. And I'll provide you some evidence for that now. So first, okay, so probably this all work, but it's probably a good moment if there are any questions about what I said so far.
Maybe if I can ask something really quick, Gabriel.
Mm-hmm.
It isn't super clear to me. So you're motivating the fact that these should be related to a spinning primary by looking at an experimental fact, right? So that you're homogeneous. As soon as you add angular momentum, you start getting vortexes. Mm-hmm. But is there some point in which maybe convince you slightly more formally, let's say, that these what you are computing are correlators of spinning primaries?
So Well, I mean, the alternate, so if the superfluid develop vortices, this is a spinning primary. So I mean, of course it's a primary because you can check that the state is annihilated by the standard generators, by the momentum, but by the special conformer, sorry. But I mean, I think it's more of, yeah, of course there is a physical assumption here. It's more like, if it is a superfluid, then you expect the superfluid to develop vortices generically. So in a generic theory, you would expect such a description to apply. And okay, experiments is for the sake of intuition, but you can take any theoretical weakly coupled model that you can imagine in which you can go to a superfluid phase and you would find vortex solution. For instance, if you take your lambda phi 4 in 4 minus epsilon, it's trivial to find some of this vortex solution classically there. And you expect them in the double scaling limit to be related to some of the states. Actually, we know it's that case.
Right.
But yeah, there is a physical assumption in that, of course.
Right.
I mean,
like, for example, you cannot recover like the spin structure that this correlator should have, right?
no, I mean, the 2-point function, so here I'm focusing on the scaling dimension, but you can compute 3-point functions I'm not going to talk about. And you can match the result to the spinning structure of correlators.
Okay, so this can be done. That's right.
Yeah. So for instance, we computed the, let me call the primary QJ. We computed QJ, J mu. It's trivial, essentially QJ, and we know that this in CFT has, I don't know how many structures, something like 1 to order 3J structure, 3J tensor structure. Yeah. And you can make predictions for the sum of these OP coefficients within the Fetty filter regime and see that the structure matches.
Okay.
So this is, yeah.
Okay. Okay. Thank you.
Well, if there are no more questions, I'll go on. But thanks for the question, actually. Okay, so again, to get some intuition on what could happen, and then it was useful to me to look at experimental and theoretical works done in condensed matter literature. Particular, it's something which I find very cool, is that once you start spinning Bose-Einstein condense even faster than the regime in which you develop the vortex lattice, and for this it's actually crucial to have a trap which is not quadratic but at the very least quartic, you develop a vortex annulus. So the density, there is like a giant vortex with an enormous core, and the density gets localized on a thin strip, which however has now a purely irrotational flow. So in this strip, there is no vortices. So this was actually, I think, first time proposed in 2003. And then also studied, actually, the most useful paper theoretical for me was this one by Fetter, Jackson, Stringari in 2005. And recently it was observed experimentally in 2019 by the Paris group. And there's also this nice non-technical review. And this is the picture, just to give you an idea of this is 50 micrometers. So, and the name giant vortex annulus comes from this community. So that's what giant means in condensed matter experiments. But it's actually very cool. So, okay, so the third question is, can something like this happen also in the O2 model? And can we see if this matches what we expect from the bootstrap? One reason to expect a transition in the O2 model a bit more theoretical is that when the vortex lattice spins faster and faster, at some point it will exceed the sound speed of the phonons. And when you have something which is spinning faster than the typical velocity of your excitations, for instance, it's known that you emit radiation and you undergo a super radiant transition. You see, the same thing which happens when you put an electron and in a medium, and you make it move faster than the speed of light in that medium. You make Cherenkov radiation, and you undergo a transition to a new state. The same thing happens here, should happen here, of course. So you might expect a transition also in this case to a new state. So, but okay, this is just some motivation. And so the reason why I'm talking is that I think there is a natural candidate for a giant vortex also in the O2 model. which when the ratio of the angular momentum and the charge is an integer number, I don't know why, but this is a technical simplification I need, just takes a simple form of a superfluid. Here I'm back to the scalar description with some alpha here behavior. I don't know how to write it. And this is just J equal RQ. So you can compute the density, and of course you find that that's this behavior here. But what's more, I think it's clear in picture. It means that you have some superfluid density in some region, and then it drops dramatically to 0. And this is analogous to having a vortex on the north and the south pole. But what's different here is that now I'll take the regime where J is much larger than Q2A3 half. And this means that the vorticity L will be of order mu. So L over R mu will be essentially 1 minus some corrections which are small in the regime J squared much larger than Q cube that I want to focus on. And similarly, even though this looks pretty much like a superfluid, the fact that this is a different behavior shows in the fact that the chemical potential now is not anymore set by the charge, but it's rather set by the ratio J over Q, which is still large owing to this condition. So this solution here, in fact, looks pretty much like the picture I showed before from the non-technical review of the giant vortex. So let's look a bit closer at what if the FT is well posed for such a soliton.
Gabriel, I'm sorry, just a quick question. I'm trying to understand the figure. The blue region.
Yes.
The blue region outside the bands. That's the vacuum, or that's the non-rotating superfluid?
Yeah. Sorry, I should have said thanks. So blue region is the vacuum, and warmer colors means you have density.
I see. So there's no charge. There's no charge stuff at all. There's no charge fluid at all in the blue region. There's
no charge fluid at all in the region. That's precisely what happens in the here. So
that's
kind of a stereographic. Well, it's a plot of the solution, but it's almost stereographic projection of this picture here.
Yeah.
But yes. So. But okay, let me explain. I think this is a good question. I was going to explain a bit clear, I think, in more in detail what this picture means. So away from the equator, so away from the region where you have some density. Now I'm going to parameterize that, but as you guess from the picture, this region here gets smaller and smaller as you increase J. The centrifugal potential goes like L squared because you have this phase spinning so fast, and divided sine squared theta, it just comes from the geometry. So you have a huge centrifugal potential, and this should gap all the excitation. So most of the sphere, you're in the vacuum. Okay, that's fine. You have a trivial effective field theory locally there, so it's okay. In the red region, where most of the density is, so the charge is localized there. And then you want to ask under which condition you have a good derivative expansion there in the bulk. And it turns out the condition is as long as Q squared is much larger than J. So you have a window. You have a window Q to the 3 half, which is J much smaller than Q squared. And why these funny numbers pop out, there is a quick way to understand it. So the size of this region here, delta, you can easily estimate it to be from the soliton solution to be Q to the 3 half over J. And I think it's natural to require that this size is much larger than the typical interparticle separation, which is 1 over the density to the 1 half, which is 1 over square root of Q. And this naturally gives you the condition Q squared much larger than J. No, this argument is clear.
Gabriel,
yes.
Could it be that this Q squared could be understood because the more you rotate, the thinner this thing becomes? It's like going one dimension less, and then you have Q squared, which is what you'd expect in 2 dimensions as opposed to 3.
That's a great comment. I didn't think about it. That's a great comment. You're saying that in 1 dimension,
Well, I mean,
So
the 3/2 becomes q squared in the one dimension down, right?
It's yeah, understand that. Could be. So because of course, I mean, as you see from these formulas, you make J larger, then the theory becomes thinner and thinner. So I don't have I didn't think about it. It's a good comment. Sounds right to me, but I don't know.
Just because I was expecting at some point you would have said that this thing becomes thinner and thinner, it becomes just the equator. That's why I was. So
we tried to begin to develop an effective field theory just on the equator, but that wouldn't be right. I think that's going to become clear when I talk about the excitation. But it could be then the regime J much larger than Q squared. That's the right thing to do. Even though there, I'm not sure you can still talk about superfluid, but the parametrics, they seems to be correct. Yeah.
Thank you.
Okay. So anyway, thanks for the question. It's a good point. I didn't think about it. Okay, but of course, I mean, more pedestrian, you can just look at higher derivative correction, effective field theory, of course. So, but physics, I think, Domenico just provided an argument, and another argument could just be just related to the size of the giant vortex region. Then you have a third region, which you might have not expected, but turns out that there is a different behavior at the transition point from vacuum to superfluid. So there is a region where the superfluid density is rapidly dropping to zero. So this means that superfluid density is not anymore the dominating quantity. What is dominating is the derivative of the soliton. So like something like d theta d chi square, or d theta of the density, if you prefer. And this means, so physically, that if there is a quantity which is larger than the superfluid density in that region, but it's still non-trivial, that the derivative expansion gets slightly reorganized near the edge. And this is very similar to what happens in non-relativistic conformal field theories and harmonic traps, where at the edge of the trap, you have a reorganization derivative expansion, or even more in rotating effective strings, where it's known that you need boundary terms whose derivative expansion is organized differently than in the bulk. And both of these cases, I think, were very cleanly analyzed in these two papers by Hellerman and Swanson. At least I found it very clear. In particular, you notice here that the steepness of the profile is set to scale, which has these weird powers of J and Q, which will bring us some important corrections in the following. So let me now go to the results. I'm finally going towards the end of my talk. So the first thing you can compute in this regime is the energy of the ground state. So, okay, this is a simple calculation. The first thing I want you to notice is that if you forget about this whole thing here, so in the limit J much larger than Q raised to the alt, the result approaches J, which is precisely the energy you expect for a multi-trace operator, which is what you expect to be the ground state from the bootstrap. So that's one reason to believe this state is actually there and represents the transition to the large spin limit. There are a number of corrections, which depends still on the same parameter alpha of the original alpha Q to the 3 half, which goes like Q cube over J square. These actually, they are suppressed in this limit, but they all arise from the leading order action, so they are all calculable. And here I just showed the first, but there are also some others which are less important. Now you might guess that higher derivative corrections will provide some new terms. The first one would go like 1 over Q, you can estimate. But actually it's a bit more subtle because now you have to take into account the fact, as I said here, that at the boundary, you have a new scale. So what happens technically is that you need to add some boundary operators in the theory that are naturally localized where the superfluid density vanishes. And this you do by adding operators of this form. And this brings in new corrections, which depends on new Wilson coefficients. That eventually you can show they lead to corrections to the energy scaling like with this weird power. And it might not be obvious, but I ordered all the corrections such that each one is bigger than the other. So if you are confused by this boundary operator, you can just think something else. You can just add by hand a kinetic term for the radial mode. So imagine that this comes from some weakly coupled completion of the theory with a radial mode, and estimates where does the kinetic term of the radial mode become as important in the giant vortex as the density, and cut off all your integrals there once you compute the energy. And that would give you the same, this would give you this same scaling here. But I'm just saying the right way to think in effective field theory is in terms of these edge operators, as Hellerman and Swanson nicely introduced. I think also Vito Pellizzani used recently. Okay, it's a technical point. What's even more interesting, I think, that you can compute fluctuations on top of this soliton. And this is a bit technically involved because to do the calculation, you have to expand again in Q cube over J square. But after you do that, and you do some gymnastics, so you do some change of variables, you get a very simple action. Y is just related to theta in some complicated way. And weirdly enough, this simple action depends only on pi dot plus d phi pi, but not on pi dot minus d phi pi. So it looks like it lacks a gradient in one direction. And this is even clearer from the equation of motion, which takes this form here for the fluctuation. And this nicely actually matches, again, what we expect for multi-traces, because in this limit, this means that just the spectrum reads a fluctuation as a gap equal m plus n. So n is any natural number, positive, and m is just the angular momentum you are adding or subtracting. So it can be negative. So if you think of your multi-trace over Q, this m and n correspond to adding derivatives, or n correspond to add boxes, and so forth, so on. And okay, if you think a bit, you realize that, and each of these operations, the multi-trace limit, they just amount of adding an integer amount of energy, just one derivative, two derivatives. So it's very nice that this comes out as a fluctuations of this profile. I should say the expansion holds only for m and n, much smaller than delta minus 2, so eventually much smaller than Q. And okay, now you might be worried because m can belong to Z, so I can add a spin minus 2 and a spin 2 excitation with n equals 0, and I'll seem to get something which is degenerate with the ground state. So you might be worried that this is actually unstable. So to this aim, you just need to restore the first correction in Q square over J square that you can compute. And you get some corrections to this formula. I won't show them here, but the point is that this entirely leaves the degeneracy. And the impact, you can predict the gap for the next steady state with the same angular momentum and charge of the giant vortex with this formula here. So it's like Q cube over J square, and it still depends on the null. So, okay. Are there any questions here before I summarize?
Yeah, can I just ask a question?
Yes.
You mentioned that there is a the EFT is controlled by another energy scale in the boundary of
Yes.
giant vertex. So is the naive bulk, by bulk I mean inside the strip, EFT, does it break down as you approach the boundary, or is it just?
So if you try to evaluate higher derivative operators, the correction from higher derivative operators to the energy, they are divergent close to the edge. So it's pretty much like it happens in relativistic CFTs.
Right.
So yeah, so that's the thing here. But again, I mean, I should say, if you just do a naive cutoff of that corrections in, based on which once you expect them not to be trustable anymore, you recover the same scaling here. So it's just. Okay, so I think it's eventually took me more time than I thought. So let me just summarize. anyhow, what I want to say now is that what I tried to convey in this talk is that effective field theory and some physical intuition provide you with a quite clear picture, or at least suggest a picture for what is the lowest dimensional operator at fixed charge and spin in the O2 model. And you can identify a number of phases like this. So for small spin, much less than square root of Q, you have a superfluid plus 1 phonon. For J in between square root of Q and Q, you will have the vortex anti-vortex pair with energy scale correction to the superfluid scale like square root of Q log J square over Q. Then you will have a regular vortex distribution until Q to the 3/2. And the main result of today was that in the window between Q to the 3/2 and Q square, you might expect a new state, which is a giant vortex state. I called it in analogy with the condensed matter literature, with energy scales linear in J and as corrections which are calculable. And finally, for Q square much smaller than J, I think you expect now a smooth transition in the spectrum to the Aldheim-Aldacena multitrace kind of operator, which again is linear in J, so it's very similar like this, but corrections are now not universal, well, are less universal and are controlled by the twist gap of the theory now. So I think this is a very nice picture, and I believe it applies in the O2 model. There are some open questions. Well, one, which I think is technically too involved, I tried a bit, is I strictly speaking only talked about J divided by Q as an integer number. I don't think this is a huge limitations because corrections away from this limit in the giant vortex, should be suppressed, but one might still want to know whether one can be a bit more precise about them. And yeah, I think it's just a technical question of finding the right soliton. It might be very hard. I mentioned that one expects a transition from vortex lattice to giant vortex for J order Q to the 3/2. And a natural question is whether one can analyze this transition at weak coupling, say in the double scaling limit in the Wilson-Fisher fixed point, and whether this is indeed a super radiant transition, as I mentioned. So if it happens by emitting many quanta as the stuff of the superfluid spins faster and faster. But again, also this might be very technically involved. I think more tractable should be the problem of studying the large spin limit rather than going from superfluid increasing J, going from the multitrace picture and increasing Q. So taking the Aldheim-Aldacena description and adding particle and see if we can learn something by doing that. And of course, the extension of these results in 4 dimensions, which partially was worked out before, but not for the giant vortex state. And that's all I wanted to say. Thank you.
Thank you very much. We don't have a whole lot of time, but maybe there's 1 or 2 quick questions for Gabriel before we go on.
Sorry, I have a question. That's Francesco.
Hi.
Ciao, Gabriel. Gabriele. Oh, Gabriel. So technically, you're talking about the O2 all the time. So if you had to consider non-abelian case, maybe because O2 is technically also the U1, so then it will probably get much more interesting or complicated, I would say, all these vortices.
So the O3, I think, is kind of analogous because essentially all it matters is the Cartan. In the O4, yes, I mean, you would have 2 gauge fields rather than 1. And well, and there you have more kind of phonons. So yeah, there the phase diagram would definitely be more complicated. I agree.
Also, and it will be also exciting in many ways since there are also many stuff coming up. But I have a question also, if I can ask a follow-up question about that. No, when you change J and change charge, right, you could undergo phase transitions. So of course you're making a certain number of assumptions on what will not happen, right? We know that often, you know, you can have, especially if you add fermions to the theory, things things can happen that changes completely the picture. So the question is, under which also goes a little bit around along the question already asked by Nicola before. I mean, under which actually solid condition one can take these limits and be sure that it's applied to the specific model at the end. Don't you worry, for example, potential phase transition in J or in Q or in the ratio of J over Q that would change dramatically the predictions?
I mean, okay, I mean, there are two phases of this question. I think one is what conditions precisely on the CFT spectrum are needed in order for any of these predictions to apply, even the simplest one. And that's, I think, is an extremely hard question. I mean, there's a work by Mujano, Giboyedo, and Jafferis about it, but I think it's fair to say no one knows precisely. I mean, more physically, however, like the assumptions I'm making are, all I'm assuming is the number of degrees of freedom which goes in the game. So I think even by analyticity in the result, you don't expect light degrees of freedom all of a sudden to get into the theory. Vortices in some sense are not in degrees of freedom, are just some specific profiles for the same light degree of freedom. So the assumption, is that there are no other light degrees of freedom which come down all of a sudden as you vary Q and J.
Or no phase transition in general that happens.
Well, I mean, there is some transition within the superfluid itself in between all of this regime. I said between these two regimes, there might be, in the macroscopic limiting where it makes sense to mention it, some unknown transition. Also in this regime here and this regime here, there is a window where no effective field theory applies. And I should say also here, so that it's not like we're excluding phase transitions. We're excluding transitions at random points, at points where nothing happens in the effective field theory naively. So we're excluding fine tuning in which degrees of freedom becomes all of a sudden light with no other reason if not tuning. And of course, I mean, this can happen, but in simple enough model, you don't expect it to happen. But I don't have any more than a physical answer at this stage.
So it's basically all based on a physical intuition. There isn't really a rigorous proof of that.
No,
so
there is no rigorous proof.
Okay. All right. But it's very exciting. Thanks a lot. I didn't want to undermine it. I want to understand better. Thanks a lot.
Thank you.
I see one more question, and we go on after that one.
Yes, hi, I'm Tassos Petko. Just a quick question. Gabriel, do you have any idea of a possible holographic dual of this whole picture of superfluids?
I mean, the one candidate for the dual of a superfluid is a boson star, which is just the global coordinate version of the holographic superconductor. And then you can start putting vortices in the holographic superconductor. But I'm not sure whether it's the only one. I actually remember you wrote us with some interesting candidate some time ago. But I think one of the things which confuses me all the time about holographic duals is that they have, as soon as you turn on a small temperature, they have large entropy. So they have an entropy going like n squared T. And this seems to contradict the intuition that you only want to have Goldstone modes at low energy, which are finite number of them, or one even in this case. So this is one of the reasons why it's hard to match with holography, that there is something about the Lagrangian limit and the large Q limit or finite T limit that does not commute, and we don't fully understand it. So, but okay, morally, the simplest dual should be the holographic superconductor.
Okay, thanks. Thanks, Gabriel.